In the last part of section 2.3 dealing with continuity, we're going to deal with the intermediate value theorem for continuous functions. So there is a video here that we're going to watch quickly dealing with this. So you can sit back and watch this video. I'll put the closed caption on so you can follow along. Okay, we saw a good video there that explained what the intermediate value theorem was all about. And hopefully this definition makes a little bit more sense. Again, if a function f of x is continuous, and that's the key on the intervals a to b, which are closed interval, then if you pick some d between the value f of a and f of b, and that value d is going to have its x value somewhere between the x values of a and b. And that's basically what the intermediate value theorem says. Now let's take a look at a few examples that deal with the intermediate value theorem. So we have h of x can be defined by the function x cubed minus 2x squared minus 4x minus 5. And the question is asking, can the intermediate value theorem be applied to guarantee a value in the interval 1 to 5 where h of x equals 0? Justify your answer. Well, first of all, before the intermediate value theorem can apply, the function has to be continuous. And we could say, since h of x is a polynomial, therefore it is continuous. And we have a closed interval from 1 to 5. So therefore, the intermediate value theorem can apply. The first thing I'm going to do is I'm going to evaluate my function at the left endpoint, which is going to be 1 cubed minus 2 times 1 squared minus 4 times 1 minus 5. And if we work this out, this ends up being 1 minus 2 minus 4 minus 5, which works out to be minus 10. If I evaluate h of 5, that's going to be 5 cubed minus 2 times 5 squared minus 4 times 5 subtract 5. And if I was to work this value out, I'm going to get, this is going to be 125. 5 cubed is 125 minus 5 squared is 25 times 2 is minus 50 minus 20 minus 5, and this works out to be 50. So if we think about this, if we were to draw a quick little sketch to help us visually, okay, at 1, my value is negative 10, and at 5, I'm way up here at 50. Again, because this is a continuous function, I have to be able to go from this point to this point without lifting my pencil off the paper. Now, is there any way I can go from this point to this point without crossing the x-axis? No. So this proves that there is a value where the function takes on 0. So we can write, since h of 1 equals 10, that is less than 0, which is less than h of 5, that equals 50, and since h is continuous by the intermediate value theorem, there exists an x 1 less than x less than 5 such that h of x equals 0. And we'll talk more about how we write this final proof after as we do more examples. But again, the idea of it is pretty straightforward. I have one value below the y-axis, I have our x-axis, I have another value above the x-axis. It has to take on every value in between, and it's asking us if there's a value where it takes on 0, and of course it does. Okay, let's take a look at another example. It says selected values of a continuous function f are given in the table. What is the fewest number of zeros of f on the interval 20 to 30? So again, it's a continuous function, so that means the graph has no breaks or jumps in it, okay? And going from 20 to 30, we're going from here to here. we have to look at the y values and how many times it changes sign. So it changes one sign at least for sure in between here, and it changes at least one sign again in between there. So if we were to look at the chart, I would say the value would, or the answer would be C, 2, because f of x changes sign between 22 and 24 and 28 and 30. So at a minimum, there's at least two places, where the function takes on a value of 0. Okay, in our next example, it says what values of the function kx, values of the function kx are given in the table. Which of the following is enough alone to guarantee of c in 4 to 9 such that k of c equals 4? Okay, so number one, which of these is enough alone on its own to verify that? Okay, that's kind of the key to the question. It has to be alone. Well, if we look at the chart, okay, k of c takes on a value of 4 two places. Okay, it takes on a value of 4 somewhere between 4 and 5, because my k of x goes from 2 to 5. And somewhere between 5 and 6, it also takes on a value of 4 because it goes from 5 to 1. And it tells us that the function is continuous in both of these places. So I would say the answer would be 1 and 2 are valid. So my answer here would be A. Okay, the last example that we're going to look at in the intermediate value theorem comes from the 2007 AP exam. And question A, again, we did this when we looked at composite functions back in our pre-calculus section, but it might make more sense now. So it's saying h of x is defined by the value f of g of x minus 6. Now, in this question, it tells us the function f and g are differentiable. Well, we haven't learned about differentiability yet, but differentiability implies that they are continuous. So we know our function is continuous. And they're asking us, the function h is given by f of g of x minus 6. So this too is continuous. And we want to explain why there must be a value r, which is really an x value, between 1 and 3, such that the value of the function takes on -5. So the first thing, again, I have to do is I have to calculate h of 1 and h of 3. So h of 1 is f of g of 1. It's kind of messy there, sorry. So this is really f of g of 1. And g of 1 from my table is 2. So this is really f of 2. And f of 2 is equal to 9. So I know the point when x is 1 on function h, the value is 9. So now I'm going to do the same thing for h of 3, which is going to equal f of g of 3 subtract 6. Well, g of 3 has a value of 4. This is really f of 4 minus 6. And f of 4 has a value of -1. So this is going to be -1 minus 6, which is -7. So h of 3 is equal to -7. Again, from a graphical point of view, at 1, it was all the way up at 9. And at 3, it's down here at -7. Because the function is differentiable, it's continuous. Again, I don't know what's going on in here, but I know it looks something like that. I should probably make it more look like a function. There we go. Passes the vertical line test. So now the question is saying, show that the function must take on a value of -5. Okay, well, again, -5 falls between -9 or +9 and -7, so it somewhere has to be, if this is -5 here, obviously it has to hit the function somewhere. Okay, so again, we can conclude that h of 1 equals 9 is less than, so sorry, is greater than in this particular, actually let's do it the other way. Let's change this, or in our explanation, we could say that h of 1 equals 9 is greater than -5, which is greater than h of 3 equaling -7. So since h is continuous and closed on the interval 1 to 3, then the intermediate value theorem applies. And then we could say there exists, they want us to use R in this case, so there exists a value R, 1 less than R less than 3, such that h of R equals -5. So again, that's the justification point. And we'll see moving forward as we prepare for the AP exam, you'll get a few of these questions where we have to apply some justification. Okay, so I think that pretty much wraps up this section. There will be a handout that I'll give to you in class that will go with this section, so make sure you try those questions on the handout. There's only 4 questions and 1 curve sketching sheet, so give those a try and see how you do.